Something I always try to impress upon my students is look deeper. Don't stop looking once you've found something interesting. There may be more there. There may be nothing more there. It's kind of like the old expression was, I found it in the last place I looked. Because who would carry on looking after you found something? Well, maybe we should try that someday. Maybe we just keep looking. Maybe we'll find something else more interesting. Anyways, today we're going to talk about looking deeper and how it helps you. The GERA Foundation presents this series called Navigating Research. When first presenting to my students, I give them this image here and ask a simple question. Which distribution is more interesting, the blue dots or the red squares? Some will say the blue dots, some will say the red squares. And then I ask them, of course, the follow-up is, why? Why do you choose that? And the people saying the blue dots will say, it seems to confirm what you're trying to do in this experiment. And those saying the red dots will say, well, they're anomalous. So why are they anomalous? And one of the questions I might ask afterwards is, why are they different? You know, if this was the experiment we're doing. Here, I show the same two distributions and I ask the same question. And now, there's nothing to suggest one is right and the other is wrong, or both are wrong, or whatever. None of that exists. So, in effect, the axes and the concentric circles acts as your preconceived assumptions of everything you're doing. And personally, this is how I try to observe things. I try to remove all of the physics. I try to look at my objects as with childlike wonder to first see the beauty of the image, to first see that, and then start seeing the distinctions between different things in the image, in the data, whatever it is I'm looking at, and that's how I do it. So I would ask this question to the students next after the first one. I'd say, which is more interesting? And of course, the answer is neither are interesting, neither are boring. They're all the same. They're okay, the distributions look different, but what does it matter? We can't tell. We don't know anything. So if you looked at this image first before the other, then you'd start asking questions, and you might actually draw your axes somewhere in the middle here, or something crazy like that, thinking, well, they're just distribution around, we don't have enough data points. It goes on. So this is a great example to demonstrate to people what their physics does to them before they start observing. They already have a preconceived idea, that then they do their observing, then they see their results being confirmed or refuted by the red dots in the case of the previous image, red squares. Anyways, so that's what this is all about. And so when you try to look deeper, you got to look beyond the physics. Well, if you got the physics front and center, you got to get the physics out of there first, right? So you got to try to look at this thing, as I've always said, as I keep saying, with childlike wonder. You got to stop seeing this from the viewpoint of a physicist and see it from the viewpoint of a child first. And then grow into the physicist you are and ask the questions, trying to explain the observation. You have to look deeper. Here's a self-portrait of Rembrandt, circa 1659. Many people have probably gazed upon this image and simply enjoyed the beauty of the picture. Here is the same picture of Rembrandt, 1659, but we're zooming in on just his eyes, and you begin to see the brush strokes, the tones, the variation of the tones, and the palette of colors that he used to make this painting. And when you look deeper, this is precisely what you're looking for. And you can look deeper still, and you will see even more. When you start talking about how to observe or how to look at things and how to find new phenomena in your data, you got to find a useful source for that. And this particular source is a star-forming region in the southern galactic sky towards our galactic center of great interest to many people, and you can see here it's being monitored by this Japanese telescope. This is data from Japan. Myself, I was actively involved in monitoring this source in the 90s, And this source was found to be rather interesting by a good friend of mine, Sharmila Goedhart. But before I carry on with this video, and before I try to use this as an example of how you can look deeper and find more, I want you to freeze this frame, if you're interested, and look at it yourself for some time, maybe a half hour, 20 minutes, 10 minutes even. Just stare at it and see if you can find things in it, and then compare it to what I'm going to tell you in a few moments. All right? So I'm warning you, freeze it now. The image I'm showing here is called a dynamic spectra. So in essence, all it is the vertical lines that you can see in the image are individual epochs of observation. So each one of them represents a squiggly line, as I call it, but a spectrum from the spectrometer at, in this case, Japan, but I did it at HartRAO in South Africa. And then I would stack them up over, and then I would get an x-axis in days, so you get a time, so you have velocity versus time, whereas the contour represents the strength of the signal in Janskis, okay? So we call that a dynamic spectra. Now Sharmila Goedhart, she didn't even bother doing this. She just simply created time series, or light curves, as the optical astronomers call it. And what that would look like in here is a horizontal line through one of these bright regions where there's a maser spot, or in this case, a velocity feature. And with that horizontal cut, you get a time series or light curve. And from that, she found that there was a period of 243 days for the source. Very interesting. But the source itself was already interesting because it was first discovered in 1991 at 6.7 gigahertz to be the strongest methanol maser. So it made it very easy for small telescopes like HartRAO or Ibaraki in Japan to observe this source very quickly and do it on a regular basis, whether it was 10 days or 1 day, what have you. So this source wanted to be found. It was very bright, it wanted to be found, and it was the greatest, it was an excellent candidate for monitoring, and therefore we were able to make images like the one you see here, this dynamic spectra, which then I would stare at for hours upon hours, and I'm willing to bet I've stared at this image, not this image, but the HartRAO data for at least 1,000 hours, because I've processed it for all sorts of other phenomena, and I'm continuing to stare at it. So this is an excellent sample, an excellent source to explain what I'm talking about when I say look deeper. As I said, it was found to be the brightest methanol maser in the galaxy. Okay, that's number one. That makes it the prototypical 6.7 gigahertz methanol maser. Number two, it was found to be periodic, and now it's the prototypical periodic methanol maser, the 243 days. Okay, so this source is interesting, and you spend a lot of time looking at it. And the more you look at it, the more you find. Thus the reason why you want to look deeper. The discovery of periodic methanol masers in this particular source, using a small single-dish telescope at the southern tip of Africa at HartRAO, a 26-meter, directly led to the resurgence in the importance of single-dish radio telescopes around the world, culminating in the formation of the Maser Monitoring Organization, a group of international astronomers working together. When one person finds something interesting in their small telescope, they tell the others, and in turn trigger experiments on the much larger, more influential telescopes, thus doing world-class science on telescopes that otherwise would be forgotten. Before I tell you what I found quite interesting in this source, I just want to point out that this is probably the prettiest images, the type of image I can create as a single-dish astronomer studying spectroscopy and looking at masers. So this is as good as it gets. If you want to see exciting photos from me, this is as good as it gets. And I would stare at images like this for long periods, and as I've said, I've stared at this one for a very long period. Now, if you've ever done those little things, those little games as a kid where you're given two images and they're asked to spot the difference between the two images, and they're almost identical. and then they get degree of difficulty gets worse and worse and worse, so they're almost perfect, except a slight line is missing. This is what we're doing here. So I stared at HartRAO data for many hundreds of hours, 1,000+ hours. And so I know every crack and cranny in this image. And the Ibaraki data has to be identical to HART. There are differences. It's more sensitive, so this flux, the dynamic flux range you can see is better. HartRAO's got a more stable velocity, so it's more sensitive to seeing velocity changes. There are some differences, but when you look at the two images, you should be able to spot the difference. But I'm going to show you what I actually found almost immediately. And here it is. Without further ado, the area in black is what I noticed, and I call it the ruler. And I call it the ruler because it looks like a ruler, as I've just shown you an example of a ruler. So it's got the gradients. You can clearly see there's two features here, one at 8 kilometers per second and one at 8.8 kilometers per second. And in the one case, you see basically the 243 days. And in the second one, you see the 243 days, but you also see other flares between the two that give you the gradient of a ruler. And I originally thought that they were subharmonics of the first period. So the period's 243 divided by 2, and it would be 121 and a half, whatever, or divided by 4, and so on. That's a subharmonic, and that's what I thought it was originally, but that is not the case. Without getting too carried away trying to explain all of this business, basically I'm showing that we see that there's different periods in the data sets. So for the 8.1 feature, kilometers per second feature, we see there's just the one period. It's primarily at 243. These extra things are just the result of the profile of the flaring event. It has a quick rise and a long tail. In the upper case, we see the period of 242 days. There's some errors, obviously, and we see a secondary flare, very narrow, at 52 days, which is the new flaring that's in the middle. We can see it here. So if you subtract that from that, you're left with just the residual, and you see only the new flare at 52 days. And it's also, because it's so narrow, we think it's sinusoidal. So we fit a sinusoid, and it too gives us 52 days. And a third method also gives us 52 days. So we're very confident we see a 52-day period that's not related to the 243-day period. And it probably tells us that two different processes are involved. If we were playing that game of spot the difference, once I've zoomed into the area of interest, it's very obvious the difference between the HartRAO data on the bottom and the Ibaraki data on the top. Clearly the Japanese data's got more sensitivity. We can see the extra flaring going on between the primary flaring at 243 days. We can't see that at HartRAO. So it's that simple. However, if you were looking at the entire data set, the entire velocity extent, all of this would be very weak in comparison to the extremely bright 5,000 Jansky-Maser feature that you see at the 1.2 kilometers per second. So really that would be spot the difference. The two areas were different. This area does not look the same as this because there's more sensitivity in the Japanese telescope. Just cool, but still, looking deeper did get us to find this. I love this example of linear versus out-of-the-box thinking, and this is a great example of, you may not imagine or may not understand why, but the character holding the ball in this particular image is the depiction of William Webb Ellis at Rugby School in November of 1823, when the ball came to him, and rather than putting it to his feet and dribbling it down the field, he decided to run towards the other team's goal line, maybe out of frustration, who knows, but it literally created the game of rugby. He took the linear thinking, which is to play soccer and move it forward with your foot, changed the rules so that he could run it forward, creating rugby. Anyways, I show this image because I'm a big rugby fanatic, and it's the 200th anniversary of rugby, and it fits with what I'm presently saying here. Somebody decided to change the rules of the game. They were playing the game and decided to change the rules, and they created a whole new sport loved by many around the world. including myself. And some of the injuries I've had, especially concussions and whatnot, helped me to forget much of the physics that I've learned to make it easier for me to look deeper into these images and not have experience any biases of the underlying physics that I was taught. So my admission to how I can do it is I bang my head a lot. Don't try this at home, kids. It's really don't. Sometimes the hard part about training yourself to look deeper at images and whatnot is you begin to lose the beauty of the image itself. And so other times it's better to just simply stand back and marvel at what's in front of you, not looking to see the brush strokes, the tones, the palette of colors used. And, that may be so, but I don't know. If you're trying to investigate, if you're trying to, push back the frontiers of ignorance or cross a knowledge gap, you simply have to. Sometimes you have to give a little and to get something more. Although I think you can do both. You have to find that balance, and that's important, is finding that balance. If you're spending thousands of hours staring at an image like this one here, then you're not spending thousands of hours with your family. You're not spending thousands of hours doing interesting other things. Right? So you got to get that balance right. That's a fact. But if you want to find things that are interesting and cool, and you've already found something, don't stop looking. Look deeper. The GERA Foundation will produce more videos like this. Please like, share, or subscribe if you enjoyed this video.